grab your notes if you haven't yet. Looking at our schedule here, I put on the board for Tuesday, we're going to plan on a 1-4 to 1-6 quiz. 1-6 is a section that we can just do in one day. So we'll do that Monday. And then Tuesday, like I said, we'll plan on that quiz. I think that is the last section of this chapter. So we'll probably end up with the chapter test sometime next week also. Just let you know, that'll be coming up here pretty soon. There are no new things to tell you here, but I do want to go through some things that I want to make sure you don't forget. You can write this down if you want. You maybe don't have to, because actually when I gave you that limit handout a while back, it was this pretty blue piece of paper. Pretty much all of this stuff up here is on here, but the lesson today is going to be putting all of our limit knowledge to use. We're going to have all kinds of limit problems. So just don't forget, the first thing you should always do in a limit problem is direct substitution. No matter what, try that first. Now, if you get the indeterminate form, 0 over 0, here are some of the other techniques that we learned. And again, this is kind of already in your notes, but just a review. You can try to factor and then see if something crosses out. If you have radicals, see if you can rationalize them. If you have complex fractions, see if you can get rid of those and then simplify. And we also had some trig identities and limits that we could apply if there's a trig function in our function. Now, third, if none of that works from above, then I would probably resort to the graph. I don't like to graph it right off the bat in case it's not a nice answer, but I think there will be some today where we need to look at the graph, otherwise we can't tell what the limit is. Okay, so we're going to go in order here. Here's the directions. We're going to start with direct substitution and just work our way down if that doesn't work. So, directions for all day today. Find the limit if it exists. Find the limit if it exists. Don't forget, we learned about those infinite limits yesterday. So that's another option for your answer. If you look at the graph, if it decreases without bound, you could say negative infinity. If it increases, you could say positive. Got a lot of stuff going on here. So this is number 1. We need to find the limit as x approaches 4 from the left of x squared over x squared plus 16. You can't cross out the x squareds, by the way. That would have to have an x squared if you wanted to cross something out, but it doesn't. So, first of all, if you remember what we learned about one-sided limits, we learned that if you can find the limit from both sides, then you can just assume that it will equal the limit from one of the sides. So on this problem, for right now, I'm going to ignore that minus sign, and I'm going to see if I can do this just by approaching 4 from both sides. Okay, so that's just a 4 right there. First thing I do in any limit problem is plug in the value of x that I'm approaching. So let's try that. I'm going to have 4 squared over 4 squared plus 16, and that is actually working. You get 16 over, the bottom would be 16 plus 16, which is 32. So simplify that, and there you go, 1/2. If the limit from both sides is 1/2, then you can assume the limit from just the left side is 1/2. So that's our answer. Even if this had been from the right side, this is still exactly how I would do the problem. If you can find the limit overall, it's going to equal the one-sided limit. Okay, well that was nice. Let's keep going here. Example 2, and it says the limit as x approaches 1 from the left of 1 over, negative 1 over x minus 1 squared. Now I'll try to do what I did on the last problem. If I can find the limit just as x approaches 1 from both sides, I can assume it equals the limit from the left side. So I take the 1 and I try direct substitution, but I get back something that doesn't work. You get a 0 on bottom. Now, you don't really get a 0 on top. It's still just -1. But a 0 on bottom could mean a couple different things. It could mean that the limit does not exist. But also, now that we know about those infinite limits, it could actually be one of the infinities. It's kind of hard to tell here. So I would probably suggest, since you can't factor, you don't have radicals, you don't have complex fractions, I would probably suggest on this one that you look at the graph. It's not really the indeterminate form, but it's still not something that's working. And so I'm going to graph this, and I'm going to see what we are working with. You can graph it too, but I'll put mine up here so we can all look at it together. And it is -1 divided by x minus 1 squared. That should be what it looks like when you type it in. -1 over x minus 1 squared. So, graph, what am I doing here? I'm coming in toward 1 from the left. This is where x is 1. So from the left, what would we say our limit would be? Yeah, it's going down all the way, forever and ever. So the answer to this one is, behind here, the answer is just -infinity. You really couldn't tell that without looking at the graph. All right, we tried to find it from both sides first, but it did not work. Any questions about example 2? Now, just by looking at that graph, if it had been from the right, my answer would still be -infinity. And also, if it had just been from both sides, by looking at the graph, both sides are going down, it would still be -infinity. All right, let me keep going here. Stop me if you have any questions. Number 3, the limit as x approaches 0 from the left of x squared minus 1 over x. X squared minus 1 over x. It's from the left again, but I can try to do it just as x approaches 0 from both sides and see what happens. But plugging in a 0 right here is going to make a 0 on the bottom of a fraction. You can't have that. So direct substitution does not work. And this can't be factored. There's no complex fractions. There's no radicals. And so here again, I think we're going to have to just look at the graph. It's not something I do first on every problem, but for the last couple, that's kind of your only option. Okie doke. Let's see what this looks like on a graph. And here's how I would type this in. X squared minus 1 over x. The only reason it was in parentheses earlier was so the whole thing was with the limit. When you type it in right here, you don't have to put the whole thing in parentheses, but I would put the 1 over x in parentheses. Some calculators will let you type in a fraction, some don't though. So I'm just gonna leave it like that. That should work for everybody. And we are approaching 0 from the left. Now here again, graphing calculators are a little deceiving. It kind of looks like it stops right there, but it should really keep going. It's going to get closer and closer to where x is 0. You can trace to some different numbers to actually see that if you want to. Maybe I'll try that. Trace to, I want something really close on the left, -0.000000001. It's still, oh boy, it's still giving me back y values. This just proves, and this is just scientific notation right here, but this is just proving that if you're really close on the left, you're still getting back y's. You're not going to get back a y if you trace to 0, because there's a vertical asymptote there. But again, it doesn't just stop there, and it doesn't just stop right there. It's going to keep going. Now, what are we doing? We are coming in towards 0 from the left. So you don't have to use that part of the graph, because that part is to the right of 0. This is coming in from the left. So what would you say our limit is? Yeah, since it goes up without bound, that is positive infinity. Now, if the minus had not been there, if it was just as x approaches 0, I'd have to say does not exist, because from the right, it was going down to negative infinity. From the left, it was going up. They have to agree if you're coming in from both sides. Okie doke. I'll keep going here, like always. Stop me if you have any questions. Number 4, I want the limit as x approaches 2 of x cubed minus 2x squared all over x squared minus 4. Okay, direct substitution. If I put a 2 right here, 2 squared minus 4, that's going to give me 0. I think you actually also get 0 on top. So it's not working just plugging in the 2. But what does it look like you could maybe do on top and bottom here? Yeah, I think you can factor. On top, let me just do one thing at a time here. I'm going to leave the limit notation out front just because we haven't actually taken the limit yet. That's not real important if you leave that part off, but when I look at the top, I can pull out an x squared, and that should leave me with x minus 2. I'm trying to factor it, and then hopefully something will cross out. Now the denominator is a difference of squares, x plus 2, x minus 2. So you should get the x minus 2's to drop out, and now it's just the limit of x squared over x plus 2. I factored, I simplified. Now I'm going to try direct substitution one more time. Wherever you see x, plug in a 2, and we're looking good. 2 squared is 4. 2 plus 2 is 4. So 4 divided by 4, that would just give you a 1. So answer by factoring on this one is just positive 1. Okey-doke. Any questions on number 4? Again, we're just kind of putting together all the stuff we know about limits so far. Number 5, I think we're about halfway there. Number 5, we want the limit as x approaches 3 of x minus 2 over x squared. X minus 2 over x squared. What should I do first? Yeah, I'm going to plug in that value for x first. Direct substitution. And actually, it works right off the bat. 3 minus 2 is 1. 3 squared is 9. 1/9. That would be hard to see on a graph. So like I always say, don't just go right to your calculator. See if one of your other methods works first. Okay, well that was an easy one. Moving on to number 6. Hello, trig function. It says the limit as x approaches pi over 2 from the right of negative 2 over cosine of x. Okay, well, I'm going to grab handy dandy here. I'm thinking about not just coming in from the right, but I'm thinking about what would happen if that was just approaching pi over 2 from both sides. If I look on handy dandy for cosine of pi over 2, cosine of pi over 2, darn it, that is 0. And so you'd have a 0 on the bottom, and that's not going to work. Again, it doesn't always mean that it does not exist. Sometimes it could be in infinity. So on this one, I think we're kind of stuck. There's no identities that you could use to simplify. You know, if there was another trig function up there somewhere, you might be able to do something with it. But there is nothing that you can do to simplify that. So I'm going to have to look at the graph. Now, I will say, just a little note here, when you look at the graph, your pi over 2, if pi is 3.14-ish, then pi over 2 is about a 1.57. So you may want to think of it more as approaching 1.57 from the right. It's kind of hard to think of it as pi over 2 on a graph because we're not counting by pi's, we're usually just counting by ones. Okie doke. Now here I go. What was it? It was negative 2 divided by cosine of x. You can probably just type it in like that. I don't think you'll need parentheses around the denominator. Oh man. Well, I'm approaching 1.57 from the right. And by the looks of this graph, this is like 1.57 right here, or somewhere around here, and it appears like there's a vertical asymptote. So if we are approaching 1.57 from the right, what would we say our limit is? Yeah, it's coming in right here, and it's going to keep going up without bound. So our answer is positive infinity. Now, what would you say if it had been from the left? Negative. And what would you say if it was from both sides? Does not exist. Very good. They have to agree if you're coming in from both sides, and this one would not agree. But all we needed here was the one-sided limit from the right. So positive infinity. Okie doke. I believe there are 2 more problems here. So let's take a look at number 7. Number 7. The limit as x approaches 0 of x plus 2 over cotangent of x. All right, well, trig again here. Let me see if I can just plug in the 0. Cotangent of 0, nope. On Handy Dandy, that's giving me the circle with the line through it. So I can't just plug in the 0. Now, you probably could type this into your calculator, but it's a little bit weird with the cotangent on the bottom because you don't have a cotangent button. You'd have to do like x plus 2 divided by 1 divided by tangent of x. That gets a little messy because of that reciprocal. So let me show you something else that you could do here to avoid, making a mistake when you type this in. I'm thinking about what 1 over cotangent is. I'm going to rewrite the numerator, and this seems kind of weird right now, but I'm going to rewrite that by just pulling a 1 out front. So I haven't really changed anything. 1 times x plus 2 is still x plus 2. But here's why I did that. Now I can pull out the 1 over cotangent of x, and I can make that tangent of x. And then on the second part here, this is still just x plus 2 on top, so I'm just going to leave that as x plus 2. Now, from here, direct substitution may actually work because it's not a fraction anymore. You're not going to be concerned about getting a 0 on bottom because there is no bottom. It's not a fraction. When you plug in the 0 right here, tangent of 0 is actually just 0. And so when I plug in the 0 back there, 0 plus 2 is 2, but 0 times anything is just 0. So I did not do that on number 6 because that was just cosine and it was easy to type into my calculator. I would only do that little trick with the 1 if it's a reciprocal because they're just kind of hard to type in. I'm not saying you couldn't graph that, but I think it's a little bit easier just to kind of break it apart and flip it over yourself. Alrighty, now last one here. This is number 8. Should have a decent amount of homework time. We have the limit as x approaches 1/2 of x squared times tangent of pi x. X squared times tangent of pi x. All right, well, first thing to do in any limit problem, plug in the value that you're approaching. Now let me show that work right here real quick. If I plug in the 1/2, here is what it kind of starts out looking like. 1/2 squared would be 1/4. Square the 1, square the 2. When you take pi times 1/2, you can think of the pi over 1. And so when you multiply pi times 1/2, it really turns into pi over 2. Now I'm looking for tangent of pi over 2 on Handy Dandy, and no such luck. That gives me the 0 with the line through it. So it was worth a shot, but direct substitution is a no-go. Now, I really don't have a fraction here where I can break stuff apart like the last one. You know, tangent, I guess you could rewrite it as sine over cosine, but I don't think that's going to help us too much. We really only like to use identities if we're going to get something to cross out. And nothing's going to cross out here. So this might be another problem where the only option is to graph. So I'm going to have to type this in. I'm going to approach 1/2, and notice it's from both sides, and we'll see what our limit is. Here goes nothing. X squared, tangent of pi. Pi's right over here above the exponent button. You probably want to use that, not just 3.14. And it was pi x. X squared tangent of pi x. If your calculator doesn't look right, you may have to switch over to radian mode, by the way. Oh my, we're looking kind of crazy up here. And I'm supposed to approach 1/2. Well, this is 0, this is 1, so 1/2 must be right in between those. And it is kind of hard to see because it's all congested, but if I'm coming in from both sides, let's see what happens. As you come in from the left toward positive 1/2, I'm going to be going up without bound. So from the left, it's positive infinity. But take a look at what happens from the right. As you approach the x value of 1/2 from the right, it's going down without bound. Those are not agreeing, so we would have to say the limit does not exist. You could do the one-sided limits. From the left, it's positive. From the right, it's negative. But from both sides, that is not going to work. Okay, I like this lesson because it puts all the limit stuff together. Instead of just doing like one little thing at a time, it's all together at once, which is good review with our quiz coming up. Let's go ahead and take a look at our assignment. It should be C26 here. From page 105 to 106, we've got numbers 37 to 47 all.